Okay, this one more example today. Oh yeah, someone asked me, will there be an assignment posted this week? Yes, because I'm going to post one this afternoon. Due next Monday, just like 2 questions or something. Okay. Okay, so here's another example. Oh yeah, and then someone asked another question, how many assignments in total? I'm going for 7. Yeah. I am pretty sure we're still on track for that. So, okay. So let's just do this quick example. Will I be using all for the 10%? I think I did not say one way or the other, but my normal plan is just to drop 1. Okay, so I'll just drop your lowest assignment mark and take the remaining 6, and that'll make 10%. Okay. So let G be a group of order 30, and prove there exists a subgroup of G with 15 elements. Now note that a subgroup with 15 elements, if such an H exists, H is automatically normal in G because the index is 2. Okay. And that is just a general, let me just state that as an aside. If G is finite, or even if G is not finite, if the index of a subgroup in G equals 2, then H is normal in G. Okay. And I guess I would say that I would encourage you to try to prove that. Okay. Furthermore, we just saw how any group of order 15 is cyclic. So this is a group of order 15, so it's cyclic, and H is cyclic. Okay. So groups of order 30 have a pretty, like there's not too many different possibilities for what they are. Okay, their structure is very restricted. Okay, so let's go back to this example. Okay, and the solution is just to use the Sylow theorems. Well, first, so we have to write 30 is just 2 times 3 times 5. So we'll just say we use the Sylow theorems. Okay, so we'll start with P equals 2. Why not? So we'll say let P2 be a Sylow 2 subgroup. Okay. And N2, which is the number of Sylow 2 subgroups, is congruent to 1 mod 2. And N2 divides 3 times 5. Because we factored it 30 into prime powers. So if you write 30 as 2 times something, it's 2 times 15. So the number of Sylow 2 subgroups has to divide 15. That tells us that N2 is either equal to 1. These two together tells us that it is either equal to 1, 3, 5, or 15. Okay. Unfortunately, there's no like arithmetic that helps us here. All these numbers are congruent to 1 mod 2 because they're all odd. Okay, so Sylow's third theorem doesn't really help us at all. Okay, so we just move on to P equals 3. Let P3 be a Sylow 3 subgroup. Now, if we look at N3, it is congruent to 1 mod 3. And N3 divides, so if we write 30 as 3 times something, it's 3 times 10. So N3 has to divide 10. So now if we combine these, the first thing says that it could be 1, 4, 7, 10, and so on. The second thing says that it can be 1, 2, 5, or 10. And if we look at the common things between them, well, so N3 is either equal to 1 or 10. And then the other prime is 5. What about that? P equals 5. And let P5 be a Sylow 5 subgroup. Okay. Now N5 is congruent to 1 mod 5. That tells us it could be like 1, could be 6, could be 11, could be 16, like that. And N5 also has to divide 6. So N5 could be 1, 2, 3, or 6. And the kind of common things are just 1 and 6. Okay, so here's our summary. N3 can be 1 or 10, and 5 can be 1 or 6. Okay, there are several ways to see why these can't happen. But probably the best way is just to do what we did before. You know, P3 and P5 are cyclic groups. So, right, P3 is generated by X, P5 is generated by Y. And then with the same argument, we can say that where XY equals YX. Actually, Actually, no, I don't know that unless I know that they're normal. So we kind of have to argue against these two things happening. Oh, sorry. Yes, that is a good idea. Look at N2. If you remember, that's the first thing well, okay, yeah. I mean, I forgot to write N2 down. The reason why I didn't mention N2 because it can be so many different things. Like the two different restrictions for N2 didn't restrict the possible values of N2 at all. So like N2 is usually just more trouble. That's all. Okay. So let's try and exclude these two possibilities. Okay. So for example, and this is like a common technique, which I'll try and describe quickly. And then probably I'll just have to continue this this example with a video because we're already kind of over. But here's the strategy. So we want to show that N3 is not equal to 10. Well, if it was 10, suppose N3 equals 10 and count the different elements of all the Sylow 3 subgroups. Of the 10 different Sylow 3 subgroups. If you count them, there's 10 of them. Each of them has the identity element, but then the two remaining elements are all different over all the different Sylow subgroups. So what you have is, among them, you have 10 times 2 plus 1 elements in the Sylow 3 subgroups. Okay, and then what do you have left? You have 9 elements left. And then what you can argue from there is that you get those have to join up to give you all the elements of order 5 and all the elements of order 2. Okay, so you do some more arguments. Okay, which I'll elaborate in a video basically. Okay. Yes. So tonight I'm going to work on this example, a video for this example, as well as a video for the solutions to assignment 3 for you guys. So please look out for that. Okay, I'm already, a few minutes over, so I'll stop there. So, yeah, I'll see you guys on Friday, unless you happen to watch the assignment solutions, and I'll see you when you watch that. See you later.